Okay, in this video I'm going to talk about the Menelaus theorem. So the theorem is very similar to the Chevas theorem that I proved in the previous video. So while in the Chevas theorem we considered the criterion when like the three lines connecting vertices of triangle connecting to the points on the opposite sides intersecting in the same at a single point or all parallel to each other. So in this in the Menelaus theorem again we have a triangle, we have 3 points at the sides or extensions of the sides, but now the criterion is not for the lines to intersect at a single point, but for these three points to lie at a single line. So basically they cannot now all be on the sides, so at least one of them must be on the extension of one side. So basically these 3 points, they lie at a single line, and so let's denote A, B, C, D, E, F. And so the theorem states that the points D, E, F are collinear, meaning that they lie at a single line, if and only if the product of these ratios, so very similar to what we have in the Chevas theorem, so BD over DC multiplied by CE over EA multiplied by AF over FB is equal to -1. So in the Chevas theorem this product was equal to 1, and here it's -1. So now I need to explain that and this is again the same as in the Chevas theorem. So here we take the vectors and not just the segments. So the ratio of BD of the vectors BD and DC, notice that BD and DC are the vectors on the same line, so they can be either in the same direction or in the opposite direction. So this is equal to either BD over DC, just the segments, or minus BD over DC. So we just introduce a sign of this ratio, and it's either plus or minus depending if BD, so this is if BD and DC are in the same direction, and minus BD over DC if BD and DC are in the opposite direction. So if they're in the opposite direction, then it's minus, then minus the ratio of the length. So, and then for this product, so basically how it's easily to remember this is we start from from a vertex of the triangle, let's say starting from the vertex B, and we go, let's say, clockwise. And we go by the side to the next vertex, and then so like by each side for each side we have a ratio here, so it's from one vertex to another, and in the middle there is another this point that is at this side or at the extension of the side. So the next one would be from C we go to E, and then from E to A, and then from A to F, and from F to B. So CE, so in the second ratio we have CE over EA, and then in the third ratio we have AF over FB. So in this manner we go like around, like clockwise by the sides of the triangle from one vertex and returning to the same vertex. So that is the ratio. Now so now let's prove this theorem. So for the proof, so actually strictly speaking, we need to consider multiple cases for this signs, like minus and plus, and carefully consider each case. But I'm going to show in detail only one case. So so let's say that we have. So let's say that the line passes the sides and the extensions of the sides exactly as shown on the picture. So, and the other cases where it passes some other way, like it could be considered similarly. The scheme of the proof is the same, like we just need to carefully adjust it for each case how the line passes, and to check the signs plus and minus. So so basically what we do is we draw a perpendicular from each vertex of the triangle to this line that passes through all these points. So yeah, so we now prove in this direction. So we assume that the lines, that the points DEF are collinear. So we assume that DEF are collinear, and we need to prove that the product of this ratio is equal to -1. So we draw perpendicular from each vertex of the triangle, and so let's denote the length of this perpendiculars as A, B, and C. Right, so now, so this is point D, this is E, and this is F. So now we have a similar triangle, so let's denote now this HA, the fit of the altitudes HB, and this is HC. So we have the triangles, so let's show them in blue. So this triangle is similar to this triangle because all the angles by two angles, basically one angle is 90 degrees, it's a straight angle, and the other angle is this there, like the angles between the same two lines, so it's the same angle. So the triangle BHBF is similar to the triangle AHAF. and from this we conclude that AF over FB is equal to A over B. Right, so the sides, this side of the triangle to this side of the triangle is equal to the ratio of the other two sides. And so similarly we have this triangle similar to this triangle. So the triangle CHCD is similar to the triangle BHBD, and from this we obtain that BD over DC is equal to B over C, and then the third triangle would be the third, like it's difficult to draw it. So one of the triangle is this one, and the other one is the large triangle. So like basically this one. Yeah. So like it would be confusing if I fill it with color, but so I just draw the sides. So basically the triangle CHCE is similar to the triangle AHAE, and so from this we obtain that CE over EA is equal to C over A, right? And so notice that these ratios, this and this are exactly the ratios that we need, only without signs. So exactly these three ratios that we need. So when we take the product, of these three ratios, so BD over DC multiplied by CE over EA multiplied by AF over FB. So in this case the vector, only this ratio is negative. So the way that the line passes, so notice that F and D are on the sides of the triangle and E is on the extension. So this ratio is negative, so it's equal to minus CE over EA, and these two other ratios are positive, so they're equal exactly to the sides, the ratio of the sides. So we can rewrite it as BD over DC multiplied by minus CE over EA multiplied by AF over FB. So this is equal to minus BD over DC CE over EA and AF over FB. Again, this is only in the case where the line passes as on the picture. So this is only one case among multiple cases that we need to consider. And so now this is equal to minus, and now we substitute these ratios with what we found. So BD over DC, so this is equal to B over C. B over C, so CE, this is equal to C over A, and this is ratio is equal to A over B. And now we notice that A and A cancel each other, B and B cancel each other, and C cancel each other. So in total we have -1, exactly what we needed. Yeah, so this proves one case. So the other cases where the line passes different ways, the sides of the triangles are considered similarly. Like the scheme of the proof is the same. So we, like in all cases, we take the perpendiculars from the vertices of the triangle to this line. So so now the converse statement. The converse statement. So basically, we assume that assume that the ratio BD over DC multiplied by CE over EA multiplied by AF over FB is equal to -1, and we need to prove that the points DF lie on a single line. So let's say that we have so A, B, C. So let me draw it specifically that they are not on the same line. So this is D, E, F. So on this picture they are not on the same line. So what we do is basically we assume this. We need to prove that D, E, F and are on the same line, collinear. So we draw the line through D and F, or let's say D and E. So we draw this line. It intersects the side of the triangle at some point F prime. So we denote by F prime the point where this line DE intersects the third side of the triangle. So if F, so basically we need to prove that F and F prime is the same point, because if it's the same point, then these points are collinear. So suppose that it's not the same point, then we can apply the statement that we already proved, so the converse statement that we just proved, to the points DEF. So we apply the already proved part of the Menelaus theorem to D, E, and F prime, and so we get that this, so D, E, and F prime, they are collinear, and so now we have that BD over DC multiplied by CE over EA and multiplied by AF prime over F prime B is equal to -1. So we compare the original equality and this equality. So we notice that these two ratios are the same in these two equalities. So like let's say when we divide one by the other, so they cancel each other, and what we get is that so from this and from this, we get that AF over FB is equal to AF prime over F prime B. So these ratios are the same, but it's like the point is determined uniquely by the ratio. So if we have the ratio, there is a unique point F that divides the segment AB in a given ratio. So if these two ratios are the same, it follows that the point F is the same as the point F prime. And so from this we immediately conclude that DEF are collinear. And this concludes the proof. So that's it for this video.